This is Physics Lab 2, E&M motor. Our main goal for this experiment was to understand how the flow of a charge through a coil creates a magnetic force, and the question we were trying to answer was how does increasing the current in a wire affect the magnetic force? There are a number of factors that affect magnetic force, the first being distance across the field, the second, strength of the force, and third, the directionality of the poles. And from this experiment, we established when you increase current, you increase the magnetic force. Our experimental design included three materials: wires, batteries, and magnets. And our experiment consisted of the following steps. First, shaving part of the circular wire. Second, resting the wire on top of a system above magnets. Third, connecting the wires to the batteries. And then we recorded the rotations per second of the wire. And then we changed the amount of batteries to change the amount of current. And we used a slow motion camera to calculate the number of rotations per second. So the right-hand rule is the basis of our experiment. It states that it's how the flow of a charge creates a magnetic field. The interaction with the magnets and the base of the motor spins this wire.
So this is our circuit diagram. We connected a 3.3 volt battery in series with our electromagnetic motor, shown in the orange box. This provided current to flow through the motor, and the magnets provided a magnetic field. The moving charges in the motor experienced a magnetic force, which drove the motor. This is the magnetic model of the motor. The motor spins because the magnetic force pushes down on one side of the motor and pushes up on the other side, as indicated in blue. This is due to the current flowing in different directions on either side of the motor. The wire was stripped completely on one side and only half on the other side. This insulation ensured that the motor only gained momentum every 360 degrees, and this momentum carried it through a full rotation. So our hypothesis for this experiment was that increasing the number of batteries in series with the motor would make the motor spin faster. The number of rotations with 2 batteries was 2.4 rotations per second, and the number of rotations with 3 batteries was 7.2 rotations per second. An important note is that we recorded the motor in slow motion, which is 240 FPS. We observed 10 seconds of each recording. Since normal video records at 60 FPS, 10 seconds of slow-mo equals 2.5 seconds of normal video, and we used this fact to calculate the number of rotations per second for each trial. We used two important equations in this experiment. One was Ohm's law, V equals IR. Resistance is equal in both settings, so since V and I are proportional, if we increase voltage, we will also increase current. The second is the magnetic force law. Knowing that we have an increase in current from the Ohm's law, we can use the magnetic force equation to prove that there will be an increase in force. This is due to the fact that they are proportional to each other.
In this experiment, we had a wire that was fully stripped on one side and only partially stripped on the other side, which is crucial to allow the loop to spin. If both sides of the wire were fully stripped, the non-stop flow of current would cause the direction of the force to flip once the ring got to 180 degrees of its original position. Since one side is only partially stripped, current stops and doesn't flow through the entire wire, so the ring reaches 180 degrees from its initial start position. It will only feel force coming from one direction. This is due to the fact that the partially stripped wire doesn't allow current to flow through, so there's no force coming from that side. For our experiment, we initially started off with 2 batteries and increased to 3 batteries. Using Ohm's law, we know there's going to be an increase in voltage. An increase in voltage would cause an increase in current because the resistance is the same between the two. Since we know there's an increase in current, we can say there's an increase in force using F equals IL times B. So the difference between a Bush motor and our model is a Bush motor has 2 sets of magnets on side. These magnets are opposite polarities of each other. Opposite charges on the magnet help the motor to spin. This is similar to one side of the wire only being half soldered in our model. If the magnets were not oppositely charged, the blades would only spin back and forth in the same vicinity. The brushes on the motor charge the commutator, which is the part of the motor that can spin. This is the force that causes the arm to spin around. The DC motor, I believe, is a more practical use of a magnets as a motor. So if we, in conclusion, increasing batteries will increase the current through the system. If we have more current, the loops will spin faster. We got 7.2 rotations with 3 batteries and 2.4 with 2 batteries. An increase in current will also cause, as we increase the current, the overall force of the system will also increase. Some of the errors we could have possibly had: we didn't account for air resistance, and we didn't account for friction from the rotation of the wire. Assumptions we made is there's no resistance within the current circuit, and that the field from the magnetic magnet is stronger than the field produced by the moving charges in the current.